All right, this is the Chapter 8 Squiggly Notes. I'm going to start with page 4 of the notes that are posted. Because, you can't see electricity and it's hard to tell what's happening, but with this mechanical system, you can imagine this thing moving. In fact, if you have a car, you could go out there and push on it and see it bounce, and or a guitar or something that's obviously vibrates. You can sort of think about and understand it better. And that's where this stuff, all this math for these vibrating systems comes from, is mechanical systems originally, because we could see them. And we saw all this math, formulas and tools were derived, and then they were applied to circuits. In fact, the circuit elements were constructed to obey similar rules, like inductors and capacitors are made to follow the same rules that we already had the math for. So just go through this thing real quick. So if you took a mass and hung it from a spring, and then took this piston cylinder thing with a fluid in here, you would end up with a spring mass damper system, where the forces on this thing when you try and move it are going to be the spring force, which is proportional to the distance, and the damper force, which is proportional to the velocity, right? And the damping coefficient is dependent on the viscosity of the fluid that's in here, whether it's like a real thick oil or water or air. Then the force due to the acceleration is the F sub m. So if you sum these guys, and I got them all going up here. I changed this from what I've posted, but if you have them all going up, now they're not all going to be up. Some are going to be up, and at least one will be down, or at least one of these will have a negative quantity. But it depends on which direction it's moving to determine which one of these is positive and negative. The mass and the damper force. I have two mass forces here. The mass and the damper force will be in opposite direction to the movement, for example. But anyway, you add up these guys and they're going to sum to 0. And I'm omitting gravity because that's counteracted by the spring preload, right? When you first hang this guy, gravity's going to be pulling it down, and the spring will deflect a certain amount, and it'll be at an equilibrium there. So we can just ignore that part of it just to make the math simpler. And we're only concerned with the forces that are acting when this thing is moving. Okay. So anyway, these are summing up the three forces on the free body diagram, and then substituting these equations in there, we get this thing. We can rearrange this so that it's in this form. Acceleration is the double derivative of distance, and velocity is the single derivative of distance, and there's distance. We call this a second order differential equation. So I find this helpful thinking about vibrations in electric circuits. Like, for example, if rho were 0, if you had no damper on this, right? This thing, and you just kind of pull down on this mass. Imagine the damper's not here, and you pull down on this mass. This thing would just bounce forever, right? So you can imagine if there are no resistance in a circuit, a similar thing would happen, and that's in fact what happens. So most systems have at least a little bit of damping. So if you do want them to bounce forever, you have to put some energy into the thing, and so that's what certain bouncing cars do to keep themselves bouncing. They're overcoming the resistance here to get this bounce forever thing. All right, so let me take a little bit of an aside to say that you need some faith here, because there's a whole lot of math and physics stuff that's going on. There's all kinds of derivations that we're gonna skip, that take too long for us to go through, and we assume that you've had them already. And then we're going to arrive at some equations that are that are useful. And so this in here, you really need to have faith that that this works. So yeah. So let's go back to the scribbles. And the equation that we're going to solve, or the circuit that we're going to solve, is a parallel RLC. That's the only circuit we're going to do. The book has series RLC, and we're not interested in that. It's the same stuff, just everything flipped. Okay, for a parallel RLC, these three elements are in parallel between nodes A and B. And there's a signal of interest, V sub t here. And that's what we're going to solve for, the voltage across all three of these guys. So this is analogous to a spring mass damper, X prime and X double prime. So this circuit is initially energized. Now remember in chapter 7 we had these natural response circuits, and we had an energizing circuit that would energize either a capacitor or an inductor, and then a switch would be thrown and they would decay down to zero. So we're going to do the same thing, except the energizing circuit is not shown, right? So somehow, by an unshown circuit, this capacitor ended up with an initial charge in it, indicated by V0, and this inductor ended up with an initial current in it, indicated by I0. And a switch is thrown, and we have this thing here, and it's going to start to decay due to the resistor. So the resistor is sort of acting like what the damper does. It's using up energy. It's acting like a little bit like what the damper does in here. So there's going to be one of three responses. There's either going to be overdamped, underdamped, and critically damped. And these are apparent by the mathematics that characterize the system. The curves are usually okay, but they're not always enough. In other words, overdamped is going to overdamped and critically damped can cross the axis one time. Both of these guys could do this thing. So they can look like they're bouncing, but they're not. So they look a little bit like they're oscillating, but they're not. So you really know from the math that whether they're overdamped or critically damped. But I'm getting ahead of it a little bit. Basically, if it goes down really, really slow, there's too much damping. Like imagine there were like molasses in here, and you pulled the spring up, it would go down really, really slow. That's overdamped. So if you have a high resistance, you're going to get an overdamped circuit. If there's air in here, or your shocks in your car are bad, all the oil is leaked out of your shocks, then and you push down on your car, it's going to bounce. So that's underdamped. Okay, low resistance value will lead to that. There's a resistance value, right, that's perfect, which is critically damped, which will cause this guy to go down to zero as quickly as possible without any bouncing, right? That's what you want your shock absorbers to be on your car. You want them to be critically damped, right? So you push on your car or this mass, you want it to come to its neutral state as quickly as possible, and it might pass zero once. All right. So the response depends on the value of RL and C, whether you're going to get a critically damped, overdamped, or underdamped response. And I was talking mostly about R and which is analogous to the damper, but L and C have an effect as well. So here's the derivation for this circuit, right? So this is the circuit's derivation for this thing, which is similar to what I showed you for this mechanical system. So yeah, so here, look, all these currents at node A are shown as leaving. Now, obviously, that's impossible. So at least one of these quantities will be negative. But we're assuming they're all leaving, so that makes them positive, just for the math. Once again, one of them will have a negative value in the solution. But anyway, You sum up the currents into the node A. It's IR, IL, and IC. Okay, IR, we have Ohm's law. I is V over R. Okay, I sub L, we have this integral here for the relationship between current and voltage. And I sub C, we have this CV prime relationship between current and voltage for a capacitor. Put those guys in there. Take the derivative all the way through. So V becomes V prime. This integral just becomes V. This derivative becomes double derivative. Arrange these in descending order of the derivatives. So you have V double, V prime, V, and then arrange the constants like this. Okay, now here's where you need a course in differential equations. So if you'd like, you could pause the video and go take a course in differential equations and then come back when you've had that. All right, I'll wait. Okay, great. So you've had your course in differential equations. Well, seriously though, that would be ideal, but if you haven't had that, just a little more faith in that these things work will get you through. So what they do in differential equations is they substitute these derivatives for these s's. So v double prime becomes s squared, and v prime becomes s, and v becomes 1. We call this the characteristic equation. And then we can do algebra on this thing. So this is a quadratic. There's a quadratic formula that this looks something like. And there's a whole bunch of manipulation and derivations that go into making these formulas. Just trust that they work, all right? So there is guessing involved in determining this solution for V. I'm not sure where the guessing happens because it's been a long time since I've had differential equations, and I don't want to pause the video to go review that. But you don't need it really. But there is some guessing, and we have this solution. So this is a general solution indicated by this 1. So V is A1 e to the S1t plus A2 e to the S2t. And the s's are the roots of this characteristic equation, more or less, with some manipulation. So S1 is this minus alpha plus root alpha squared minus omega 0 squared. And S2 is the same thing but with a negative sign here. And this comes from the solution to this quadratic, but with some manipulation to get these guys over here to look like this, which is a more useful way to think about these things. So alpha is called the Neper frequency. It's 1 over 2 RC. And alpha squared is the resonant natural frequency, omega 0. It's 1 over root LC. So this is pretty important, the resonant natural frequency, okay? Omega 0. Things want to vibrate at certain natural frequencies. A good example is a guitar string. You know, it's tuned to vibrate at a certain frequency. Everything, all the strings have a particular natural frequency that they want to vibrate at. And that's true for everything, not just guitar strings. Every object will want to vibrate at a certain natural frequency. It's just that their damping may be different. You know, most objects are damped such that they're not going to vibrate. Yeah, so this is the general solution. We can modify it for our 3 cases of whether it's overdamped, underdamped, or critically damped by looking at the s's. All right, so that brings us to the most important page probably in the notes that you need is this thing. All right, so there are 3 cases that we're going to use, and then I'll show you some tricks. All right, so it's either going to be overdamped, underdamped, or critically damped. So how do you know? You know by looking at the roots. So the roots S1 and S2, which are the roots of the characteristic equation. We call them the roots. If they are real and distinct, then the thing is overdamped. What is real and distinct? Real and distinct is something like 4.2 and 2.4. These are real numbers and they're different. They're distinct. If that's the case, then it'll be overdamped. Also, if this is the case, then this thing will be greater than this thing. So you can look at these two things, or you can look at these two things and determine if it's overdamped. If it's overdamped, then our general solution has this particular form. All right, it's the same, but we use A's instead of whatever we were using over there. No, they were A's over there too. So it's just the same. And we have these additional two equations that are true. We're skipping all the derivation, but these two equations are useful for determining usually the constants. Well, the thing is, you're going to have knowns and you're going to have unknowns. Some of these things will be known, and then you'll solve for the unknowns. But anyway, the initial voltage in the system here is the sum of these two constants, and the initial change in the voltage, or does V prime at 0, is this thing. And that can be used to solve the system of equations. So this is for underdamped, when this thing is decaying very slowly. All right? If S1 and S2 are complex conjugates, and what's a complex conjugate? A complex conjugate is something like 4.2 plus 2.4J and 4.2 minus 2.4J, where J is the square root of minus 1. J is just like I in regular mathematics, but for us, I is current. So we have to use J. Anyway, these are each one of these is a complex number, right? It has a real part and a complex part. And this whole thing is a complex number, and this whole thing is a complex number. These two numbers are complex conjugates because they differ only in their sign, all right? So if the S1 and S2 are numbers of this form, then it's underdamped. And it will also be true that the magnitude of alpha squared will be less than omega 0 squared. So if that's the case, then this thing is underdamped, and our general solution from back here, what you do is you go find a genius like Euler, and he has this identity which is just magic, right? And you apply that identity to our general solution and do a bunch of manipulations, and you get this guy. Faith. Have faith. But this guy here, so you have these two trig things, cosine and a sine, and you have omega d is the frequency. It's the damped frequency, all right? And there's two trig functions here, cosine and a sine, which could be simplified with a single sine wave, but it's broken up like this because it makes the math easier to solve for these b's, all right? But it's really just a single sine wave under an exponential decay envelope. That's what's shown over here. So you have this sine wave that's wiggling around at omega d, the damped frequency, okay? It's wiggling around, and it's underneath an exponential decay envelope, where alpha now, the same alpha, which was called the Neper frequency in the general solution. Now it's called the damping factor, right? And you have all of these equations, which are true. So V0 is B1, and this one here. These are, just think of this as a system of knowns and a system of equations where you're going to have knowns and unknowns, right? But this thing here has this shape. That's important to know. It's good to think about this damping frequency, damping factor envelope, and the damped frequency under here. And then remember the shock absorber thing. If you have no damping, it will vibrate forever. That's also true here. If you have, if this alpha, if R were 0, right? If there were no resistance in the circuit, this thing, if there were no resistance in the circuit, then alpha will be 0 because alpha is 1 over 2 RC, and so this guy here will be 1, right? This envelope will be 1 because e to the 0 is 1, and omega d will be omega 0, which we call the resonant natural frequency, right? Back from here. So if you have no resistance in this thing, then you'll just get a thing that's oscillating forever, and the frequency omega d will be the natural frequency omega 0. Okay, and that means that this thing here is not exactly the natural frequency. It's off by a little bit. So that's the vibration part of this thing. Now, if you like this stuff, there are upper division courses in vibration that you can take, which are fun, and they go through a lot more derivation and get a lot more tools. There's one in the mechanical engineering department, but I'm sure there's things in electrical as well. Okay, the last case is critically damped, where S1 and S2 are real and equal. What is real and equal? Real and equal is something like 4.2 and 4.2. Okay. If that's the case, then these two guys will also be equal. And in this case, solution 1, our general solution, fails, and more stuff in differential equations. You have to go back to differential equations and pull this guy out. This will be the solution for critically damped. This is our system of equations that we have, where you just kind of take it on faith that this works, and think of it as you're going to have knowns and you're going to have unknowns, and use this as a toolkit to solve for what you need. But we can think about the shape of the curve a little bit, like this. It's going to go down like this most of the time, but not necessarily always, because think about the first one, t e to the minus alpha t is 0 here. It's like a line multiplied times an exponentially k. So it's going to want to go up, but then e is going to win. It's going to go down like that. And the second guy, e to the minus alpha t, is just going to go down like that. So when you add these two together, it depends on what the relative contribution from each of these is. The d2 and the d1, I'm not sure where d1 is exactly, but the d2 is here and the d1 somewhere. It depends on which one of these is stronger. And these guys are going to work together or fight each other, depending on whether you're an optimist or a pessimist. And you could get different curves. Like, they're all going to start at d2, but they might go down like that, or they might go down like that. So what I'm saying is that a critically damped system, it can cross the the time axis, once. That's possible. Whereas the so this is critical. Whereas the overdamped, this one up here, if you look at the two roots, the two terms here, they're just e to the they're going to be e to the, these are real numbers, so e to the alpha t. So you're just going to get two guys that look like this, and one of these might decay faster than the other, and it's possible one of these could be negative and going up like that. So once again, you can get a cross of the not a bounce, but you could get a cross of the axis. It's still going to decay to 0. All right. So what I'm saying is, overdamped and critically damped may cross the axis once. So they look like they're bouncing maybe. So the way to tell is by looking at the roots, applying these properties here to the roots, and then you'll know if it's overdamped, underdamped, or critically damped, and then you just use the right set of equations. All right, this is the most important piece of paper in the notes, but I've got some tricks that I want to show you. All of the problems that we're going to solve in this chapter use variations of these techniques in here, right? 1, 2, 3, and 4. Okay, this is what it boils down to: figuring out which set of math you're going to use, right? just trust that these guys work. Figure out which one you're going to use. It's always going to be the same circuit, this parallel RLC circuit. Then there's 4 tricks. So one is we're going to do KCL at node A. We're just going to sum the 3 currents. And the second trick is these 2 guys. I sub C equals CV prime. The current in a cap is CV prime. This prime thing is one of our toolkit equations, right? And the current in a resistor is V over R. That's Ohm's law. The third trick is these initial conditions, which we may be given or maybe have to solve for. V0, the initial voltage across these 3 guys, and V prime at 0, which we might be given. Or you might be able to get from here, right? Here's V prime at 0, right? The other thing is these 2 guys, the natural frequency and the Neper frequency. These 2 dudes are defined in terms of R and C and L, right? This guy is 1 over 2 RC, and this guy is 1 over root LC. So, and these are related to each other, right? Sometimes they're equal to each other. For the case of one of these guys, watch the critically damped. These 2 guys are the squares of these guys are equal, right? So these are related to each other, and you can be used to solve for things. These are the 4 tricks that we're going to do. All right, so I'm going to work 3 or maybe 4 problems: a critically damped, an overdamped, and an underdamped, and then something that's just kind of a review. All right, thanks.